SwayamPrabha. Digital India. Educated India.
So, let us continue our discussion on the formability testing of sheet metals. So, today we are going to discuss about two important, rather three important subtopics relevant to formability testing of sheet metals. Okay, one is how certain important properties or parameters affect forming limit curve in general. Okay, independent of any material chosen or something like that. And the second important one is we are going to discuss briefly about some theoretical models, okay, available for evaluating the forming limit curve of any sheet. And then we are going to briefly discuss about how to detect or identify necking. Okay, what are some standard methods or procedures to evaluate or to identify necking of any sheet. This is what we are going to, these three subtopics we are going to discuss in formability testing of sheet metal. So, in the previous module we discussed elaborately about what are the different formability testing methods available. So, it could be your stretchability or deep drawability or stretching cum drawing, or it could be your in plane strain tensile test or tensile test. Okay, so limit dome height test, okay, Marciniak stretch test. So, different varieties of formability test we have studied. So, now all this formability test is going to give you forming limit curve, which we know what is it, okay, and forming limit diagram, we know these two. Okay, what are the what is a definition of a forming limit curve, forming limit diagram, we know that. Now, like your stress strain behavior, okay, like materials stress strain behavior, your forming limit curve, okay, will also be affected by certain important properties. We will discuss one after another, but in general, okay, in general we are going to discuss. This is first one, which is we know that it is a strain hardening exponent. We say n, isn't it? So, we say sigma is equal to k epsilon power n, and this n is what we call it as a strain hardening exponent. And we have already derived a equation relating n to instability, isn't it? We have also derived before that epsilon u is equal to n, which tells the fact that okay, your uniform elongation will be affected by strain hardening exponent, and the larger the n value, larger would be the uniform elongation. Okay, so which in a way tells the fact that your ductility can improve. Okay, so similarly, if you want to know the effect of n value on the forming limit curve, theoretically it can be estimated, and in general one can say that with increase in forming limit, with increase in n value, or forming limit improves. That means, so this is the forming limit curve. It is plotted between epsilon 1 versus epsilon 2, and you will see that for larger n value, let us say 0.3, you will have forming limit curve like this, but for lower n value like 0.15, you have a forming limit curve like this. Okay, so forming limit curve improves with increase in n value, but of course the effect is very clearly seen in your FLD 0. This point, no, we said FLD 0. This is very clearly seen in the case of FLD 0 and in the stretching side generally. Okay, so what does it mean? That means if a forming limit has improved, means there is a large region in which you can accommodate safe deformation. Okay, which means your formability is actually improving. Okay, FLC is moving up, means your forming limit is actually improving, because you can put more safe deformation to the material before it reaches the final stage, or the final component is made. Okay, but the prior processing may affect the quality of sheet. Okay, for example, cold working. Okay, so by cold working you strengthen material that can there are a lot of chances that your n value can reduce, which means that it is difficult to form the component, And moreover, we also know that this plane strain mode of deformation. So when you go along y-axis, you reach the forming limit curve at this location, isn't it? So this particular location is actually a conservative window for your forming limit. Okay, so in such type of materials like code work materials, better to deform it in the stretching strain path, so that you have more extra window for deforming the sheet to make the component. Okay, so this is one important parameter, and the effect of n can be understood just by relating your uniform elongation with n. Okay, so generally with increase in n value, your forming limit is going to improve, which means that formability will improve. So the next important one is called as rate sensitivity. Okay, m. So we say the strain rate sensitivity index m. Okay, this comes into picture when you go for, let us say, C epsilon dot power m, and we have also studied that this m actually controls the post necking behavior, that is epsilon u minus epsilon t minus epsilon u. That particular region in the stress strain behavior it is going to affect. So which means that this m is going to control the growth of neck. So okay, once instability is started, how quickly it can grow or how slowly it can grow will be controlled by this m value. So the rate sensitivity effect, it affects the rate of growth of neck. Okay, but generally you will see that this m value does not affect, okay, will not have much effect on the tension at which its maximum value is reached. Okay, so it is going to have effect after that. Okay, so now if these two diagrams, if you see, it will tell you in general about the effect of m value, and you will see that higher the m value, you will have better forming limit as compared to material with lower m value. This is where we were discussing about superplastic materials. Okay, superplastic materials or superplasticity is a property, okay, which will have ductility of several hundred% as compared to the conventional materials, right? So higher the m value, you will see that generally your forming limit improve, mainly because you can delay the growth of neck. But it may so happen that for materials which have got a higher m value, your plane strain may not have be closer to n value, it will be larger than n value. You can see that lower m, I am saying n here, which is what we studied, which we discussed in the previous section FLD0. Okay, but for higher m value, it may not be n, actually it will be better than n. So you have better window for in plane strain also. Okay, so you have a material with one particular n value, but the same material has got a larger m value, then you may have little bit more window for safe deformation even in plane strain. And this diagram is a well-known diagram for us. You are monitoring epsilon 1 versus epsilon 2 in the A region and in the B region. So again, we are going back to the A region, B region. We know the meaning of A region and B region, right? So A region and B region are nothing but your neck region and the outside region. Neck region, outside region. Okay, A region being outside region. Okay, so we were discussing that you will have a thickness imperfection or the region where necking happens, right? So this region is actually, you can call it as B, this region is, you can call it as A. Okay, and then we said that we can give sigma 1 versus sigma 2 and see how strain evolves in these two locations. We have discussed in the previous section how necking occurs in biaxial stretching. So okay, so we consider the same geometry and we will see when necking happens at B, okay, what happens to this epsilon 1 versus epsilon 2 in A and B region for two materials, one with higher m and one with lower m, one with higher m and one with lower m. So there are four curves here. Okay, two curves for A and B and two for two materials, higher m and lower m. And you will see that actually you have to monitor epsilon 1 versus time and epsilon 2 versus time. Okay, these two have to be monitored and you have to plot at a common time how epsilon 1 and 2 varies at two different locations. One is A and B. Okay, so you will see that for higher m, okay, this dotted line is for B region, that is where necking is going to happen, and you will see that it is for A region, and you will see that when compared to A region, B region will have unstable growth in your strain. Okay, unstable growth in strain, especially epsilon 1. Okay, sudden growth, unstable growth after a particular stage. You will see that this your A region will try to grow in the same direction, whereas you will see in the B region there is unstable growth in the limit strain. Okay, and so naturally this indicates that B is the source of neck. At the same time, you will see a lower M value material. So lower M value material means this one B, and you will see this A. Okay, so you will see that in the A region there is not much difference. A region there is not much difference, but in the B region you will see that this unstable increase will happen bit early. So which also means that you may reach limit strain little early as compared to higher M value. Okay, so that is the main difference between a material with a higher M value and lower M value. So the growth of the evolution of A and B is going to remain same. Only thing is difference in lower M value is the unstable growth happens little bit early, which indicates that its overall formability is going to be over because it has got lower M value, and you will see that the saturation happens little early, whereas in the case of higher M value you will see the saturation happens little late, and then there will be unstable growth. Okay, so that's what is going to happen in A and B region with respect to M, and we also studied this effect of M, okay, with respect to imperfection. Okay, we derived the relationship between the change in strain rate, okay, with respect to M. So previously we derived it. Okay, so larger the M value is better because it's going to control the post necking behavior. Okay, it will delay the growth of neck. This imperfection, okay, inhomogeneity we say, or F, which is nothing but that imperfection factor we said. F is nothing but we said TB by TA. Okay, TB by TA, and of course this is very theoretical in nature. Okay, so practically we don't speak anything like your inhomogeneity or TB by TA, or you have sudden change in thickness the way we have seen here. Okay, sudden change in thickness. Okay, this is TB, this is going to be your TA. Okay, this type of things we are not going to see practically, but theoretically if you want to simulate what is happening in the actual material, then you introduce this F. Right. So we also discussed that this inhomogeneity factor, or F, or which discussed about the imperfection, which defines the imperfection in the material, is equivalent to all the imperfections in the material, including structural and geometrical heterogeneities. So we understand that intuitively, like greater the imperfection means there's large difference between thickness in B region as compared to A region. Okay. So you can imagine that larger the imperfection means, let us say TA is, let us say 1 mm, okay, and TB is, let us say 0.999 mm. There is another case where it is 0.95 and it is 1. Okay, so that means this has got more imperfection, right? So greater the imperfection, you will see that lower will be the limit strain, because the weaker region is actually very weak as compared to the other case. Okay, so this what we know conceptually, schematically I have drawn this. This is with respect to large imperfection, okay, which means that your forming limit is going to come down. Okay, small imperfection means a better formability is obtained. So with the large imperfections, the plane strain, limit strain may be less than the strain hardening index also. Okay, so which means that theoretically when we say this FLD0 would be equal to N. Okay. So as per our previous discussion, it may not be in the case of materials with large imperfection. Okay, that means what? It may not even reach N value. It may fail before that. Okay. So other than thickness imperfection, we can also have practically you will see that inclusions or there local reductions in strength due to segregation of strengthening elements or texture variation. These are all other situations. Okay, which one has to take care. Surface roughness also plays a bigger role. Can be connected. So how do you relate the surface roughness of a sheet to formability? Is through imperfection, is through defining this kind of F or imperfection and homogeneity factor. Okay, they can be related. Okay, so but only concern here is surface roughness, the units. Okay, the values are going to be very different as compared to the actual thickness of the sheet. So this TB, TA, we are all TB value is going to discuss will be of the order of sheet thickness 0.9 and 0.95, whereas surface roughness you will see it's going to be a small value, but in a way surface roughness can be connected to this inhomogeneity factor F. Okay, so in that case other than thickness heterogeneity, one can see practically there are other inhomogeneity in the material like inclusions or local reduction strength due to segregation of strengthening elements, surface roughness. Okay, at one particular location it is very rough. okay, the sheet is very rough, okay, then that means at that location imperfection could be huge, could be severe. So which means that that type of materials may have less formability because of presence of large imperfections. Okay. So but we should understand one particular fact, that this type of changes, this geometric change, structural change, are actually gradually available in the material. Rather in our discussion, rather we actually take sudden change in thickness. Okay, this is a sudden change in thickness, that's what we discuss. Okay, which is generally not seen in materials. There will be gradual variation in thickness or other structural heterogeneities in the sheet. So one should be careful with that. This anisotropy of the sheet, which we generally quantify by R, that is nothing but plastic strain ratio. Small r or capital R, either way is fine. So true width strain divided by true thickness strain, and if it is equal to 1, we say isotropic. If R is not equal to 1, we say the material is anisotropic in nature, right. So now this effect of anisotropy or plastic strain ratio is a little it actually changes from the way we use theories, some theories. Okay, it is not very straightforward. I have shown you some examples here. Okay, because these are all theoretical forming limit curves. Okay, we use some models and then we calculate the forming limit curve from this, which means that during such calculations we may assume some yield function, like for example von Mises yield function we have studied, right. So like von Mises yield function, which is meant for isotropic materials. There are several other yield functions meant for anisotropic materials. We will see some of them later in the course. In a very summarized way we are going to discuss, and if that yield functions are going to change in the theoretical estimation of this forming limit curve, then that will have significant influence on studying the effect of influencing the forming limit curve, okay, because of change in R. Okay, so you have to choose this anisotropic yield function wisely to study the effect of R on the forming limit curve. Okay, so in general, if you see, in general the existing data tells that this FLD0 from experiments, suppose you have FLD0 means, again I am telling epsilon 1 versus epsilon 2 you have, this is your forming limit, this particular point is FLD0, that is your epsilon 1 comma 2 in plane strain, because it is a conservative location now, so we are taking it as a reference actually. So if you take that in y axis and R in x axis, say let us say it varies from 0, 1.53, let us say this R value, okay, then you will see that this theoretically, okay, you will see that this FLD0 actually improves. Okay, say for example at about 1.5 it is about your FLD0 is about you can say 0.2 is about, it could be about 0.4, okay, your major strain, that means epsilon 1 is about 0.4, and if it is about 2 you can see it is about 0.5, and is about 3 it is closer to 0.6. So increase in all value generally has got a positive influence on your FLD0, but it also depends on the yield function. As I said, there are two examples given here. Okay, so of course if you want to study the effect of R value, naturally you cannot use von Mises yield function because it assumes R is equal to 1, this case. Okay, so naturally we have to go for other yield function which has got which is meant for anisotropic yield function. There are several such yield functions. One famous one is called as Hill's 1948 yield criterion. Okay, one important yield criterion is actually called as Hill's 1948 yield criterion. Actually this von Mises yield function is a case of Hill's 1948 yield function. We will discuss about that later. Okay, and if you use this type of yield function, okay, then it will have some effect. I have given that here from this particular book. It is discussed more. You can look into it. And instead of this yield function, Hill's 1948, if you use a higher exponent yield function, okay, we will see that higher exponent yield function, then the effect is actually different on the forming limit curve. That is given in this second diagram. Okay, so you will see that forming limit curve for few R values I have given. So R is say 2, 1.5, 1.5. So this is isotropic, you can say. You reduce it and then you increase it. Okay, you will see that how forming limit curve is going to change on the right side of the forming limit diagram, mainly on the right side of forming limit diagram. You can see that epsilon 2 is only positive here. Of course, epsilon 1 is always positive. Okay, that is the way we draw it. Okay, so if you see that R value is going to affect in this fashion. Okay, so there is a large difference in your limit strain value when you go for the 45-degree line, let us say balanced biaxial stretching like this. Okay, large difference 1, 2, 3, 4. This points has got large difference in forming limit. But if you go closer to plane strain in this direction, you will see the windows actually reduce. The difference is actually little between these. Okay, so in Hill's 1948 yield function, there are some values which you can fix. Say for example, for this particular calculation, like n value of 0.2, m value of 0, and this f value, the inhomogeneity factor, is kept as 0.98. So when you do that, you get this particular type of curve. Suppose now if we change the yield function to higher exponent yield function, okay, what is it we will see later, then the effect of R value is something like this given here. You can see that. Again, this is also positive minor strain, and of course positive major strain. You will see that. Okay, so R value has got no effect. It is going to reach the same forming limit curve for different R values. You can see R is equal to 0.5, R is equal to 1, R is equal to 2. R is equal to 0.5 is a circular filled circular one. So these values are coming here somewhere. Okay, then open square is also here. Okay, which is R is equal to 1, and your filled square is also here. Okay, there is not much difference. There is no difference between these forming limit strains. Okay, it comes with the same forming limit curve. It falls on the same forming limit curve. And for this calculation in the yield function, they have used, let us say A is equal to 6. There is a parameter called A which is kept as 6, and n value as 0.2, same as this, m as 0, same as this, and f is little bit increased. Instead of 0.98, we have used 0.995. Okay, so the effect of R value is little tricky, and it depends on the yield function you choose. Okay, because different yield functions have different accuracy of predicting the forming limit strain, and two such examples are shown here. Okay, so the next one, there are two important parameters. One is called as a temperature, the other one is a strain rate. Okay, so this, of course, this strain rate effect can be connected to m. Okay, strain rate effect can be connected to m. So that's why I've given here two or rather three graphs. Okay, this is effect of strain rate. Okay, this is effect of temperature. So these are all strain rate values. These are temperature values given here. So when you study the effect of strain rate, temperature is kept constant. Let us say it is kept at some degree centigrade. Let us say maybe 150 degrees centigrade. Okay, you are keeping, and then you are doing forming, using some formability tests, and then you are getting forming limit curve. Okay, so that means the forming limit curve has been obtained at a higher temperature. Let us say not at room temperature, maybe like warm forming or hot forming like that. So in that situation, if you see increasing the strain rate, it is 0.1 per second, 1 per second, 10 per second. Okay, so that means you are increasing the forming speed actually. Okay, you are increasing the forming speed actually. Okay, this is slowly deforming. This is the highest speed, and this is in between. You will see that your forming limit is actually coming down. Forming limit is actually decreasing. The difference between black, red and blue. If you see that for higher strain rate, you have a lesser forming limit, and this depends on the m value of the material. And if you take the other effect, suppose you keep it at one particular strain rate. Okay, let us say strain rate is maybe 1 per second. Okay, strain rate is fixed at 1 per second, let us say, and then you are changing the temperature. Okay, so one forming limit is for 200 degrees centigrade, which is better than the other case, which is say for example 125 degrees centigrade. This is just a schematic I am drawing. Okay, it may not be exactly like parallel in both the locations, in both the regions. One has to evaluate it and check it. Okay, so you will see that generally increasing the temperature improves the forming limit in this fashion. Okay, at a constant strain rate. But there are some examples which I have shown here. You will see that practically, okay, they have evaluated the theoretical strain rate dependent forming limit diagram for this particular material, one particular grade of copper. If you see that what are the strain rates? One, for example, strain rate is 0.01, okay, then 10, then 100, then 500. Okay, so it's more like a dynamic forming limit type. Okay, dynamic testing type. Okay, and you will see that with respect to change in strain rate, your forming limit actually improves. Okay, so probably one has to look into the materials of how is it behaving, and probably the strain rate is too high. Okay, strain rate is actually too high, okay, to show some better effect on the forming limit. Okay, so you can see that the diamond one is here, that is 10 per second. Okay, square one is 100 per second, and strain rate is, this is 500 per second. This is pretty high for your strain rate, and the forming limit is quite high in that case. So it also depends on the material. So one has to be a little bit careful how to understand this effect. Okay, but otherwise generally this is the shown by effect of temperature and strain rate. So UTS and total elongation. Total elongation effect we already know. Okay, total elongation effect is already known. So quite naturally, larger the total elongation, it is expected that forming limit will also improve. Your FLD 0 again is considered as a reference for us because it is in plane strain. Okay, it has got a conservative window, and lots of experimental data has been taken from various data, various literature. Okay, and if you plot everything together with respect to the materials total elongation, that means you need to know total elongation of variety of materials, and for the same material you should have data for FLD 0. And if you plot it, they have an exponential fit in this fashion. So increase in total elongation will actually improve the FLD 0. You can see from here to here it has improved. Just schematically I have drawn, and you can see that one can fit this type of equation for that. FLD 0 is A exponential B epsilon t minus 0.3. Epsilon t is nothing but total elongation. FLD 0 is nothing but limit strain in epsilon 1 in plane strain deformation. So this A and B can change depending on the materials that you choose. Similarly, UTS can also be quantified, how it's going to be affect the FLD 0, and again here lots and lots of experimental data has been plotted in one graph, and you will see that it is also an exponential one, but it is going to decay. So increase in UTS will actually reduce the forming limit curve, Okay, so FLD 0, I have just given a simple equation. FLD 0 is nothing but P plus B exponential minus S into sigma UTS, where P, B, S all are fitting constants. They are actually fit constants one has to get after fitting. After getting all the data, let us say you have 100 data for this. Variety of materials are evaluated, okay, and you are putting all the data, and then you are going to fit it, then you will get this equation. Okay, so you have to be a little bit careful when you increase the UTS of a material. In a way it's good, but generally otherwise you will see that its FLD can come down, okay, following this particular. It is just not a linear decrease, it is exponential decay, one has to be careful. Okay, and total elongation, if it improves, it's good that FLD 0, there are chances that it may improve by following an exponential increase. So N, M, strain rate, temperature, then R, then you have epsilon T, sigma, UTS. Okay, these are all certain important properties that we get from tensile test. Okay, some are actually working conditions. Say for example, strain rate and temperature are actually working conditions actually. Okay, but otherwise N, M, R, epsilon T, sigma, U, these are all material properties which will affect the either the forming limit curve in both the regions, positive minus 10, negative minus 10, or in FLD 0. Now this sheet thickness, if you see, it is actually not a material property, rather it is more like a geometric property of a material, and it is sheet thickness decided by the application. Okay, so and then whatever sheet thickness that we are discussing in general is of the order of, let us say, maximum say 2.5, 2.8 mm, 3 mm, like that, not more than that. Okay, so and what is the effect of thickness? That can be explained from this particular simple schematic. Okay, so you can see that of course there is some data also available for you, we can check it. So x-axis is N, strain hardening exponent. This diagram is drawn not only for thickness but also for N. So x-axis is strain hardening exponent, y-axis is as usual our FLD 0, okay, and thickness has been found to increase in this fashion. You will see that this is 0.5 mm, 1 mm, 1.5 to 2.5. It means that other than N and thickness, all other properties of the material are kept constant or assumed not going to vary. And you will see that with increase in N value 0, 0.05, 0.1, 0.15, 0.2, 0.25, you will see that there is a significant increase in FLD 0 at any thickness. This is what we have seen before. But of course, after a particular value, let us say it is going to become saturate, it is not going to show big effect, okay, which is we have seen before. And the effect of thickness, which is the main purpose of this graph, is also coinciding with the effect of n value. So, larger the thickness, you can say 0.5, 1, 1.5, 2, 2.5, you compare 0.5 and 2.5, 2.5 has got very high, okay, FLD0 as compared to 0.5 at any n value you pick up. You take 0.1, you go along this line, you will see that it has got, this fellow has got about 0.2728, whereas this fellow has got only 0.1. If you pick up 0.2, here you have got only 0.22 maybe, but here you have got about almost 0.55. Okay, so increase in thickness actually improves the FLD0, which means that even in plane strain condition you can have a better formability if you replace 1 mm thick sheet by 2 mm thick sheet for a particular application. Okay, assuming that n is not going to change. If n is also going to be increasing, then it is favorable for us. Okay, so instead of reaching this particular point in 2 mm thickness, you may reach this particular point in 2 mm thickness. Right, so that's the effect. So increasing the sheet thickness, what happens actually? Why it is? Because increasing the sheet thickness, you will see that the neck becomes more diffused and localization would be delayed to reach necking stage and to reach the critical depth. So it will take some time, it will delay. The larger the thickness, the extra thickness that you provide actually can delay the the necking stage and then a critical depth to reach a particular depth, the neck has to cross the entire thickness, no? So that will be a little delayed. So there are chances that your FLD0 or FLC0 can improve. So we also have something called pre-straining the sheet. Pre-straining the sheet means, I hope you remember an equation where we introduced epsilon naught for describing the flow stress. So sigma is equal to epsilon naught plus k epsilon power n. We might have seen that this in 1 or 2 problems we worked out here, isn't it? So which means that if you put k is 0 here, still you will have some, So if you say sigma is equal to k epsilon naught plus epsilon power n. So if you put your strain as 0 here, so you will get some strength in the material, which means that this equation will take care of any pre-straining that you have in the sheet. So now this pre-straining also may have some effect on forming limit curve. Okay. So that means you have to purposefully pre-strain it and then see how it is going to affect, and that is what I have given here in this schematic. So what does that mean? That means there are 3 forming limit curves here. Okay. So one is no pre-strain, the black color one is no pre-strain, okay, which means that the material is actually coming to you and then you are using a forming limit testing method like hemispherical dome test, and you are getting this forming limit curve without any pre-strain. But you can purposefully pre-strain it in 2 different ways. Let us say, for example, you are using uniaxial pre-strain. Uniaxial pre-strain means you take that material and you pre-strain it in the strain path coinciding with uniaxial type of deformation up to a particular strain, up to a particular epsilon bar, let us say. So up to a particular epsilon bar you are deforming the material and then you are evaluating the forming limit curve using any test procedure. Okay, then you will see that in the uniaxial pre-strain, okay, the forming limit curve is going to change in this fashion, the black color one to red color one. You will see that your plane strain location is actually moved, okay, and then it looks like there is some slight upward movement of forming limit curve. And the same thing if you do it totally opposite to that. Suppose if you are pre-straining in equibiaxial tension, equibiaxial plane strain, that means on the extreme right of your forming limit diagram, okay, then you will see that the green color one is going to be the one, your black color forming limit curve is going to become green color, where you will see that specifically your plane strain has moved towards the right side. Okay, so this also you can strain up to, let us say, one particular epsilon bar value, some epsilon bar value, okay, but you have to pre-strain in such a way that some formability exists in the material. Okay, so you should not exhaust the forming limit fully. Okay, so before going for actual evaluation of forming limit curve, so one has to do that appropriately and then get the forming limit curve. One can get like this, but one can bring in this equation into forming limit estimation and you can virtually change this epsilon naught to get the forming limit curve. So that is another way to get it. Okay, so your pre-staining the sheet also has got effect on forming limit curve. So these are some important your material properties and geometric properties of the sheet, and testing conditions like pre-strain, temperature, your strain rate, okay, all are going to affect the forming limit. And of course there is one more important parameter, that is nothing but your coefficient of friction mu. Okay, coefficient of friction, okay, Coulomb's coefficient of friction, isn't it? Coefficient of friction, or practically speaking whether you lubricate it or not. Okay, so you use a lubricant, so lubricated condition or dry condition. Okay, lubricated condition or dry condition. So this I think we have studied in the previous section, that generally this whether you put dry situation or a lubricated situation, when you evaluate forming limit curve, it is not going to affect the forming limit, rather it is actually going to change the strain path only. Okay, so that means suppose if you have a forming limit curve like this, so epsilon 1 and epsilon 2 you have, and this forming limit curve is a material property, right? So if you get this particular forming limit, and you will see that when you change the friction coefficient, it will rather have an effect like this. Okay, so suppose you are using dry condition, you will reach the forming limit here, you will reach the forming limit here, let us say a dry condition, I am just putting, or you put any lubricant you want and you change the lubricant to some other lubricant. Okay, so we don't know the characteristics of the lubricant, we don't know mu, so that if that is the situation, then still one can study the effect. So for one particular case you will reach a forming limit. In this case, if you change the lubrication, okay, let us say lubrication is better, then you may get a higher limit strain, okay, you may get a higher coordinate, but at the same forming limit, okay, you may get a better epsilon 1 star and epsilon 2 star value as compared to the previous one, but it will reach the same forming limit. So basically it is actually changing the strain path from one beta to another beta rather than forming limit itself. Okay, so your epsilon 1 change will get adjusted with respect to change in epsilon 2. Okay, accordingly you will get the limit strain. So individually you will see limit strain may change, but then it will finally lead to the same forming limit. That is why we always say that the forming limit is actually a material property. So that is the effect of mu. There are a lot of discussion in the subject about effect of mu, but in general this is the way it is going to work. So after studying all these parameters, let us quickly in a very summarized way, let us discuss some important theoretical estimation of forming limit curve. Okay, theoretical models. Okay, there are several theoretical models, simple ones we have already discussed, one or two before, two complex ones, okay, which will give you a forming limit curve theoretically. Okay, of course all have to be validated by doing some formability test at lab scale to get the forming limit and compare it. You have to validate it. If you go for a theoretical estimation of forming limit curve, you will see that these forming limit models can be divided into two parts. One is your analytical model, other one is semi-empirical models. So analytical models are based on some physics. Okay, like you put a lot of equations, we already derived one, isn't it? You put some conditions and then apply some boundary conditions and then see. Finally you will get same epsilon 1 star comma epsilon 2 star, and then change the beta values or alpha values in the equations to get the forming limit curve for the entire list of strain paths we studied. So that is analytical models. There are semi-empirical models. Semi-empirical models means basically models based on some fitting. Okay, basically models based on some curve fitting. Okay, so like the way we studied the effect of UTS and uniform elongation, total elongation, right? So similarly you can also estimate forming limit curve or data points in that using semi-empirical models. So first let us see few analytical models, simple ones only we are going to discuss, and we are not going to derive the entire equation here, rather we are going to discuss all these things in a very conceptual way. Okay, what is the basics behind it, that way only, instead of theoretical derivations. So a lot of derivations are available in textbooks and papers, one can look into it, or any plasticity book can be referred for that. So when you come to analytical model, the first one is basically we already studied for tensile instability, that is your considerate condition. Okay, and we know that any material which undergoes plastic deformation, there are actually two domains in that. One is a stable plastic straining domain, other one is a unstable plastic straining domain. Stable plastic straining domain means hardening is influenced, okay, on the tension force, okay, but not the cross section reduction. Okay, that is going to be actually your initial part of plastic deformation, which we say it as a stable plastic deformation. And then once you reach one particular stage, after that if you see, it is going to be unstable plastic straining. If you see in that location, in that region, the material hardening, okay, cannot compensate the decrease in tensile force due to severe reduction in sample cross section area. Okay. So, your hardening is actually going to help the tensile force to improve in the first zone, but in the second zone you will see that the hardening actually is not going to compensate the decrease in load, okay, which is going to actually happening because of a significant reduction in area of cross section. This finally will lead to a typical stress strain behavior which we have seen. So, now given that situation, this transition is going to happen at one particular place, okay, from stable plastic response to unstable, okay, and at that stage we can say that it can be said that onset of necking corresponds to maximum tension force, and it can be written mathematically as dF is equal to 0, and simple derivation we have already shown. It can be shown that 1 by sigma d sigma by d epsilon is equal to 1, okay, or d sigma by d epsilon is equal to sigma, and if you put this particular power law equation and then if you derive it, we can show that epsilon u is equal to n, or we can say epsilon bar is equal to n. It means that as per this condition, for a sheet obeying this particular law, okay, we found that the material starts to neck when the strain equals a strain hardening exponent of that particular material. And we have also seen that if you do not use this equation, if you use pre-strain equation, this equation can be modified by including some factor of pre-strain into it, isn't it? Some factor of pre-straining into it. And if you will see that if you include some pre-strain value, it is going to be a subtraction that is going to play a role here, and hence you will see that your forming limit, your instability strain or necking strain is going to actually decrease, right, that we already studied. So, this is one important analytical model that people use to estimate your tensile instability. Now, the next important model is called as a Swift model. Okay. This Swift model can be used to obtain limit strains epsilon 1 star and 2 star by using considered criterion in biaxial tension side. Okay. Instead of tensile instability, you can apply this in biaxial tension by taking a sheet element loaded along two perpendicular directions. So, you take a sheet element, okay, and you load it along two perpendicular direction, which means biaxial tension, okay, and you apply this considered condition. So, after that what do you do? Apply considered criterion in each direction, okay, along one direction, let us say along two direction, you apply this particular condition, and of course, one can put similar condition. Your dF is equal to 0, you can say. Similarly, you can put conditions on both the directions, and if you assume the same power hardening law, sigma is equal to k epsilon power n, you will get two important expression, one for epsilon 1 star and epsilon 2 star, right. So, epsilon 1 star and 2 star are nothing but the data points on the forming limit curve. Okay, this is epsilon 1 star and 2 star, another epsilon 1 star, another epsilon 1 star, another epsilon 1 star, right. So, this is a general equation one can get, expression one can get for epsilon 1 star and 2 star, okay, and here you will see that in this equation, okay, your sigma 1, there is sigma 2, sigma 1, sigma 2 are there, these are actually principal stresses, and you will see that there is one more, the two more, one is your F. This F is not your inhomogeneity factor, rather this F is actually yield function. Okay, this is the same F that we use in normality condition. D epsilon ij is equal to dou F by dou sigma ij into d lambda. That F is nothing but this yield function, and this n is nothing but our own strain hardening exponent. Okay, so you will see that now this limit strain epsilon 1 star and 2 star that you get using this Swift model is simple to use, but it depends on the yield function only. It depends on yield function only. And of course, it depends on only one material property, that is n. That is because you are going to use this particular hardening law, and it does not have any other forming parameter, only n is available. So, this becomes a function of n. So, now what we can do is you can use a variety of yield functions in place of this f, and you can derive this equations, actual equations for epsilon 1 star and 2 star, and finally you will see that epsilon 1 star and 2 star could be a function of your n, which is already there, maybe strain rate sensitivity index, and of course plastic strain ratio also you can include, because you may use anisotropic yield function, and of course it will be a function of alpha, so that you can get for different alphas what are the forming limit strains. Okay. And if you use Hill's 1948 yield function, okay, this is the famous yield function. If you use that equation in place of f, okay, then you will get a nice epsilon 1 star and 2 star expression. Okay, and you will see that, as I just now said, it becomes a function of r and alpha and n. So of course the Steinhorn-Ingler does not have m, so m fellow, this m fellow will not come here. Okay, so this is a simple expression. You will see that 1 plus r into 1 minus alpha into 1 minus 2 r by 1 plus r into alpha plus alpha square divided by 1 plus r into 1 plus alpha into 1 minus 1 plus 4r plus 2r square divided by 1 plus r square alpha plus alpha square into n. Similarly, epsilon 2 can be estimated from this. 2 star can be estimated from this equation. So what are the material properties you have? There is only one quantity plastic strain ratio which quantifies the degree of anisotropy. There is one parameter n, Steinhorn exponent. Other than that, you have only alpha to change the stress ratio or to change beta. So now for a constant n and r, okay, let us say r I am going to fix as maybe let us say 1.5, okay, and n I am going to change, let us say 0.2, 0.25 and 0.3. Then one can get variety of values of epsilon 1 star and 2 star for different alphas. So alpha also is going to change from the leftmost side, okay, for the the negative minus strain to positive minus strain. So I can get different values of alpha which already defined. We already discussed 5 different alphas, right? So all these alphas can be substituted here and you can get a forming limit curve. So by calculating epsilon 1 star and 2 star for different alpha, we get the whole necking limit curve or forming limit curve. Okay, these equations are simple to use because it depends on only one material property, two material property r and n, and which means that if r is equal to 1, if you put r is equal to 1 in both the equations, that it will turn out to be for forming limit is meant for isotropic sheets, okay, for the same n value. So you can take r is 1.0 and you can get the effect of 0.2, 0.25, 0.3. So then the entire value data forming limit curve is for isotropic sheets with a different n value. So this model is easy to use, and then similarly there is another model called as the Hill's model. Okay, and this Hill's model, it is going to assume something which you already discussed. In uniaxial tension test, we have also proved that the localized necking develops along a direction which has got some orientation with the loading direction. Correct, that we have discussed when we try to prove that in biaxial stretching there is no definite theta, and that is why your necking is not going to be rapid, rather something is actually delay the necking process, right? So that is why it is creating difference between experiments and maximum tension line on the right hand side of forming limit diagram, correct? So at that time we have shown that there is a definite theta existing for uniaxial mode of deformation, right? I think we have put alpha value as some value, one particular value, and then we got theta. Similarly we did for plane strain also. So localized necking develops along a direction which has got some orientation with the loading direction, okay. So but Hill's model assumes that the necking direction coincides with the direction of zero extension, and straining in the neck is due to only sheet thinning, okay. So it is going to assume that there is one particular direction of zero extension, and moreover because of that in the neck region only sheet thinning is going to happen, and further it is going to deform, it is going to fracture, okay. And with this assumption one can evaluate epsilon 1 star and 2 star, and finally you will get epsilon 1 star and 2 star as this particular equation. You will see dou f by dou sigma 1 divided by dou sigma 1 plus dou f by dou sigma 2 into n. Similarly epsilon 2 star is dou f by dou sigma 2 divided by dou f by dou sigma 1 plus dou f by dou sigma 2 into n, whereas f is our own yield function. And if you combine these two equations, you will get this particular equation. This equation is already known to us, isn't it? Epsilon 1 star plus 2 star is equal to n. So if we add these two, it will lead to our own the previous equation, which will give you maximum tension line, Okay. So, now in this equation, as per this equation, you can simply say that your FLC estimated from the Hills model above equation does not depend on yield function. Okay. So, though you are using yield function here, finally, okay, you will see it is going to depend only on the n value and nothing much is going to happen, and this equation epsilon 1 star plus 2 star is equal to n is nothing but it is going to cut your y axis at n value. Okay, epsilon 2 is 0, so epsilon 1 star would be nothing but your n value. Okay, so as per this equation, it is going to depend only on n value and not the yield function at all. Okay, that is what Hills model is going to tell you, and this method is already discussed by us slightly before. The concept is already introduced to you. Okay, Marciniak-Kuczynski model. This model is in short called as MK model. This is very famously used to predict the forming limit curve of any sheet material in this particular subject, and this particular model basically assumes that necking is generally initiated by geometrical or structural heterogeneity in the material. That we already know, that we already introduced this. Okay, you have geometrical defects, okay, like for example sheet thickness change. Suppose you take a sheet of 2 mm thickness, we say, okay, we take a sheet of let us say 2 mm thickness, but it is not going to be 2 mm everywhere. So, here it could be 1.98, 1.99, 1.985, here it could be 2, 2.01, 2.22, 2.05. So, it can vary within a small region. We say 2 mm plus or minus some value it can change. That sheet thickness change itself is sufficient to create a thinning, severe thinning at one particular location, which can lead to significant necking, localized necking. Okay. So, that is the whole idea here of telling sheet thickness changes. Of course, lattice defects are already there, they are called as structural defects. Okay. So, as per this particular theory, we are going to assume a sudden change in thickness, okay, to estimate limit strains. This particular figure, this we already introduced to you. However, we should know that the such type of changes is not actually true in practice. It is going to be a gradual change in practice. That is why I have given you different values here. So, it is not going to be a sudden change, but this is the simplest choice we have. This is the simplest choice. That is why we always say that the thickness difference is equivalent to the thickness difference that you are going to create, the imperfection severity that you are going to create is equivalent to all the imperfections in the material. Okay. So, that is the meaning here. So, this is the simplest choice we have. The simplest choice is given in this diagram. So, this is a geometrical assumption of MK model in a sheet. So, A and B belongs to the same sheet, okay, which has got same material properties, but only thing is your B region has got lesser thickness, let us say TB, when compared to TA. Okay. And your one direction and two direction is going to coincide with the principal directions as per this particular one to start with. So, sigma 1 is going to act in this direction, sigma 2 is going to act in this direction. So, if you know TB and TA, you can create this F. This F is nothing but our inhomogeneity factor, your non-homogeneity factor, which you already introduced, the TB by TA. Sometimes in the biaxial stretching, when we discussed about, we also introduce F naught, which means that TB naught divided by TA naught. That means the initial one. So, your F can change during the course of deformation. That is what we were discussing. So, we introduce this F. Okay. So, we introduce this F, which is nothing but TB by TA. So, now what we can do is you assume that let us take a case where you can do, let us say, modeling of this. So, you have some equations for all this. Okay, we can put lot of conditions to it, and then like you can find out some equations, and in that equations or in any other way, assume that we are going to monitor, okay, epsilon 1 A and B. Okay, epsilon 1, that means along this direction, along one direction, okay, in A and in B. You are going to monitor these two. That means your major strain in A and B can be monitored. Okay, so now we are going to say that when this particular ratio reaches a critical value, for example 10, okay, I am writing epsilon 1b, epsilon 1b divided by epsilon 1a is greater than 10. Then I am going to say that localization occurred in B, okay, which is an indication of onset of necking. Okay, which is indication of your necking of that particular sheet. So, I am going to simply monitor epsilon 1b with respect to epsilon 1a. Okay, once it reaches 10 or just crosses 10. So, I am going to say that the material is going to neck. Okay, at that stage I am going to pick up epsilon 1 star and 2 star closer to B, probably in A. okay, closer to B probably in A, okay, to call it as a limit strains. That you have to do this exercise, you have to do it for all the strain paths, let us say all the beta values. Okay, you will get a forming limit strains, forming limit curve or neck curve. Okay, so you will, this is what I have depicted in this particular diagram. You will see that you are monitoring epsilon 1A and 1B, okay, and you will see that in the A region, that is you are outside the neck region, okay, you are going to have some saturation, whereas in the B region, you see that it will keep on growing, okay, and one particular location you will see that if you find out the ratio, then it will reach 10. At that time you pick up epsilon 1A star, you pick up epsilon 1A star, okay, and there will be a corresponding epsilon 2A star, and these two together will form one coordinate in the forming limit curve. Okay, that is what I have written here, and by changing the strain ratio from 0 to 1, okay, so again we are looking at 0 to 1, okay, let us say this is epsilon 1, this is epsilon 2, 0 to 1 strain ratio 0 means in plane strain, okay, to 1 that is balanced by axial stretching, you can get different epsilon 1 star and 2 star, and you can connect all these values. Okay, let us say you have 4 different cases here, and you will get the forming limit curve on the positive major strain of FLD like this. 1, 2, 3, you are going to get this brown color line, which we are going to call it as a forming limit curve. Okay. So, in this zone of FLD, that is in biaxial stretching side, in this side, the orientation of the geometrical non-homogeneity, that is this thickness reduction, this orientation, you see that, this orientation with respect to principal direction is assumed to be same during the entire deformation. To start with, it is same. Okay, that means this orientation is like this. This orientation is exactly perpendicular to your one direction, and that is going to remain same, okay, throughout the course of deformation. That is what is given here. Okay. So, now you have got a forming limit curve on the right hand side of your forming limit diagram by changing, by monitoring your epsilon 1A and epsilon 1B. Okay, and you have got various values, and you have got this particular forming limit curve. Now, who will get a forming limit curve on the left hand side? The left hand side maximum tension line, if it is sufficient for us, then that is sufficient, which you already discussed. But if you want to use this MK model, then there has to be some slight change in the concept. So, here what the issue here is, you are going to monitor the same strain pattern the same way by changing the orientation like this. I just given a schematic here, the same A region, B region, this also A region, but you will see that the orientation of imperfection is at some angle, let us say phi, with respect to the principal directions 1 and 2. That is why I have created 1 dash and 2 dash. This 1 dash 2 dash are actually local coordinates for this imperfection. The original coordinate is actually 1 and 2. Okay. So, this is what you are going to do it on the left hand side. So, MK model can be extended to negative minus strain region of FLD, that means on the left hand side, by having some orientation for the imperfection with respect to principal directions. So, in this figure, this model is actually called as a Hutchinson and Neal model. In short, it is called as HN model. Okay, it is MK model, but it is modified one for the left hand side, and it is called as a Hutchinson-Neal model. So, I will not go into the equations and discussion. Only thing is, I have written two important equations here. One, how this phi, this angular orientation is going to change with strain. The orientation of imperfection varies with strain as per this particular expression. Tan phi plus d phi is equal to 1 plus d epsilon 1a divided by d epsilon 2a into tan phi, and f, which you are going to assume Tb by Ta, may also vary as per this particular law. F by f naught is equal to d epsilon 3b minus d epsilon 3a, where d epsilon 3 is nothing but your incremental thickness strain. Incremental thickness strain in B and A region, B and A region. Here also A region, so this is A region. Okay. So, what is F by F naught? F is your current value of your inhomogeneity factor, and F naught is your initial value of inhomogeneity factor. So, this ratio actually depends on this particular one. Okay. So, of course, one can apply a lot of theories, different sets of equations in it. Finally, you may get one simple model to calculate the forming limit curve on the left hand side also. So, that one can refer these books or other papers to get into it. So, now there are some semi-empirical models. What are the semi-empirical models? These semi-empirical models are handy. Okay, the semi-empirical models are actually handy in nature, you can get a quick guess of what is the forming limit curve of these materials, any sheet grade materials. Of course, they have some constraints and lot of validation is required to use that in actual practice, but this will be useful for us to quickly use in shop floor. Okay, instead of too many calculations and effect of parameters, all those things on the theoretical estimation of forming limit curves, one can use the simple empirical models to get the forming limit curve. So, I have introduced three important semi-empirical equations. There are few more available in actual thing, but one can look into it if you are interested. So, the first one is called Keeler-Brazer model. Keeler-Brazer model. This Keeler-Brazer model, again, like the previous examples, it is going to estimate FLD0. It is going to find out FLD0 in percentage. The equation is 23.3 plus 14.13 into T whole into N by 0.21, where T is our standard thickness of the sheet and N is the strain hardening exponent. T is the sheet thickness and N is the strain hardening exponent. Okay. So, as per this equation, your FLD0 depends only on N and T, and this equation is valid only for thickness less than 3 mm thickness, and that is what we are also discussing. Okay. And once you get FLD0, so again you will see that epsilon 1, epsilon 2. So, you get FLD0 from this simple equation. You can put any T and N. Let us say N values may be like 0.15 and T as let us say 1.5 mm. So, you substitute it, you will get FLD0 and it will be a 1 point in this particular forming limit curve. So, now if you want to get the left hand side of the forming limit curve and the right hand side, you can use these two equations. Okay. So, left hand side of the equation, if you see that of the FLD, if you want to get data points, you can use epsilon 1 is equal to FLD0 minus epsilon 2. So, whatever value you are getting here, you subtract epsilon 2 virtually, take different epsilon 2 values, keep subtracting it, you will get epsilon 1. So, you may get a curve like this, and on the right hand side also same thing can be utilized, 1 plus FLD0 into 1 plus epsilon 2 power 0.5 minus 1. So, epsilon 2 you can vary virtually, okay, on the right hand side of the FLD, and you will get epsilon 1. So, you may get a curve like this. So, finally, you will see that you will get the entire forming limit curve using this. There are other models which are little bit more complex. They try to bring in more material properties into it. Say for example, this particular model, they evaluate again epsilon 10 means FLD0. That means epsilon 1 in plane strain mode of deformation. You can calculate it from this equation. You will see that the equation is actually cubic form. Okay, A into epsilon 1 minus n cube plus B into epsilon 1 naught minus n square plus C into epsilon 10 minus n minus 10 into mt equal to 0. Okay. So, you will see that here you have A, B, C are actually fit constants for the material, and the material properties are actually you have n strain hardening exponent, you have brought in m also strain rate sensitivity index, and of course, sheet thickness is also there. Okay. So, for a particular value of n, m and t, okay, one can get A, B, C such that you will get epsilon 10 to satisfy this particular equation. Okay. So, from this you can get FLD 0. So, it is done. Okay. So, then a modification in this is also provided, and here you will see that this is a cubic form of equation. The same A, B, C are there. You have a strain hardening exponent. You have mt. Other than that, they have brought in R value also. They have brought in R value. The form of the equation is almost same. The cubic part is same. The square part is also same, and this part is also same. Okay, minus you have mt in place of before mt you have R. Okay, so if you put R is equal to 1, okay, you may check whether it may lead to the same equation or similar equation where R is your plastic strain ratio. You can check it. So, these are certain semi-empirical models available for us. Okay, so now analytical models are done, semi-empirical models are done. There are various other analytical models available. So, there are damage theories, damage models which can be used to get sheet fracture strains. So after necking, one can go for fracture strains also. Okay, so that fracture limit curve can also be obtained. Okay, then one can go for this kind of semi-empirical models, which are very handy and useful in actual industry practice, but validation is important for us. Okay, then the last subpart in this particular module before we go into problem is basically necking identification methods. Okay, so you are doing deformation and you are identifying necking, but there should be some standard ways of identifying that yes, necking has happened or not. Okay, so because I may say that like necking has happened, somebody else may say that no, necking has not happened, let us deform it by another 0.2 mm or something to enter into the onset of necking. So how do you identify neck? Okay, practically. Okay, so experimentally, of course, you can see the seat and then you can say that yes, necking has happened, or you can touch it and see. But which not actually possible in theoretical estimation. So how do you identify necking? So there are 3-4 methods available, but I am going to explain you only 2 methods which are simple to implement. One is called a slope method, or you can measure thickness reduction rate in this. Measuring thickness reduction rate in this. So what do you do in this? Actually, you have to follow this particular graph. This graph is between epsilon in general strain with respect to time. With respect to this is actually time, not thickness of the sheet. It is actually time here. So basically, you are going to monitor strain throughout the entire process duration. That's the meaning here. Okay. So what do you do here is, so let us say for example, at one particular sheet element, okay, we can monitor epsilon 1 and 2 and 3. Okay, let us assume that we can monitor epsilon 1 and 2. So numerically you are getting epsilon 1 and 2. A continuous change in epsilon 1 and 2 with respect to time. Epsilon 1 versus time we already discussed. Epsilon 2 versus time is obtained. For the same time interval, epsilon 1 and 2 will give you epsilon 3. For volume constancy, you can get epsilon 3 also. So now if epsilon 3 is known, then you can you can evaluate thickness reduction rate. You can get thickness reduction rate. Okay, thickness reduction means how much thickness is reduced with respect to a particular time. So that can be plotted with respect to time itself. That's what I have shown here. Okay, so there are 3 curves in this. One is your epsilon 1, which is nothing but your major strain. Other one is epsilon 2, which is nothing but your minor strain. And then you can see there is one plot for thickness strain, but from thickness strain you can get a thickness reduction rate, and it will look like this curve, red color curve. This red color curve is nothing but thickness reduction rate curve. So there are 3 thickness reduction rate. So now what you can do is like you can draw the slope lines. Okay, you can draw this slope lines from the initial part of the thickness reduction curve and the unstable part of the thickness reduction curve, and you can find out this intersection point here. You can see this black color line and this black color line are actually slope lines for this part and this part, and they meet here. This intersection point, is finding it is going to be very important for us. Okay, this intersection point is a point at which strain localization happens, and that is why there is a sudden increase in your thickness reduction rate, and there will be a corresponding value of epsilon 1 and epsilon 2, which you are going to call it as epsilon 1 star and 2 star. This epsilon 1 star and 2 star is nothing but your forming limit strain at that particular beta value, strain path or strain ratio. So you have to repeat it for various beta values and monitor the same thickness reduction rate. Okay, and the corresponding epsilon 1 and 2 where this intersection point happens would be your epsilon 1 star and 2 star. You can get the forming limit curve for the entire material, Okay, so basically you take a sheet, one particular strain path, you have to monitor epsilon 1, 2 and 3. Okay, and then from epsilon 3 you can get thickness reduction rate, and you will see that this slope, if you draw for the stable and unstable region, it will have an intersection point. The intersection point is going to tell you which epsilon 1 and 2 you have to pick up to call it as epsilon 1 star and 2 star, which is nothing but your limit strain of that particular beta value, and you can change the beta value to get different limit strain values. This is one way. There is another method which is also easy, that's called time dependent method. This is a similar one but slightly different. Okay, you will see that in this method you have to choose 2 locations. One location is a neck zone a neck region which I have schematically drawn here. This is a neck, this is a neck portion. This entire constriction is actually called as your neck. Okay, so it may not be like this, but I am just showing a case. Okay, so you have to choose one element or a location where you can measure strain in the neck zone, and immediately just in the vicinity of the neck zone or just outside it, you have to choose another location. Let us call that this is N and this is O. Okay, N is a location or element in the neck region. O is a element or location just outside the neck region. Again, what you need to do is you have to monitor strain in that location and strain rate in that two locations. So I have drawn a graph between in y-axis you have epsilon 1 and epsilon 1 dot. Epsilon 1 dot means strain rate, major strain rate, and of course this is your time, process time. Okay, so you will get two curves actually. These two curves are represented by epsilon 1 neck, epsilon 1 outside. Okay, you can call it as epsilon 1 N, this is epsilon 1 O. Okay, that means epsilon 1 neck is nothing but how epsilon 1 changes with the time in this particular location, neck zone. Okay, epsilon 1 outside means same epsilon 1, how is it going to vary? Just outside the neck zone, that is this O region. So these two are monitored, and we already discussed that in the outside region it has to saturate actually after some time. You can see that both the regions are equally deforming, and after some time you are going to have saturation in epsilon 1 outside location, but in the neck location it is going to unstably increase. It is going to unstably increase. But only thing which you have to be cautious is which location you are going to pick up for this O. That is very important, because neck zone you can somehow identify because it is a small constriction, it may develop, or there will be some severe contour, deformation contour may develop. Okay, so but this outside region, which location you want to choose, this region or this region or this region, one has to be very, very careful. Okay, so now these two curves are obtained. So now what you do is you have to get how this d epsilon 1 outside changes with the time. That will give you this red color curve. So that is why I have written d epsilon by dt. Basically it is d epsilon by dt, it is strain rate only. Okay, strain rate only, major strain outside. Outside location, whatever major strain you have, variation. For this variation you are going to get the slope and you plot it with respect to time. So epsilon 1 outside, how is it changing with respect to time? You will see that at one particular instant it will keep on increasing. At one particular instant it will be reaching a maximum or a peak, and then it will decay actually, and then it will decay. So this peak value is what you have to pick up. So the maximum point is identified as the stage of localized necking. At this particular time, the corresponding major and minor strains denote forming limit strain. So you can draw a vertical line to hit this portion, which is nothing but your epsilon 1, okay, and then the corresponding epsilon 2 together will give you a forming limit strain. Okay, so to keep it little bit more conservative, you can also choose the outside region also as a reference, and you can get epsilon 1 star and 2 star. Okay, so this diagram is going to give you only the variation in major strain and major strain rate, but then if you know the stage at which you have to pick up epsilon 1 and call it as epsilon 1 star, at the same stage you can get epsilon 2 star for that particular location. To keep it more conservative, better to refer the outside region as a location for evaluation. Okay, this is another way to locate your necking stage. Okay, so we stop here and then we will discuss further in the next topic.